Welcome to another exciting video on motion graphs. This time we're going to talk about velocity time graphs. Now the velocity time graphs are set up and they can look very similar to the position time graphs. So I guess the most important thing that you've got to ask yourself when you're doing a question on motion graphs is, am I talking about position of an object with reference to an origin, or am I talking about the object's velocity? Surprise, surprise, velocity time graphs actually deal with the object's velocity, and they can look very similar. It's easy to make mistakes, so it's important you know which graph you're actually referring to. Okay, so for the purpose of this velocity time graph, I'm going to break down the different sections, and I'm going to use a trusty helper, which in this case is going to be a panda. We're going to suspend truth and reality for a little bit of time and pretend that a panda can move swiftly around. Let's just say the panda is not only eating bamboo shoots and it can move swiftly. Okay, so the first section is on the graph is between 0 and 2 seconds. You'll notice that it's velocity plotted against time, so we're really referring to velocity, not the position against an origin. So between 0 and 2 seconds is the green part of the graph. We can see that the velocity is steadily increasing. So the velocity at this point appears to be increasing steadily with a slope. And this means that the velocity is changing uniformly. And that when velocity is changing, we've referred to previously that is the same as saying that it's accelerating. Okay, so in the first part of the graph, the panda is accelerating. So panda starts from 0, starts out very gingerly, and starts accelerating to a point where the velocity is 4 meters per second. Okay, so it would start slow and then start accelerating. Between 2 and 4 seconds, the line is flat. We've got a horizontal line. Now in a PT graph, that would mean that the object is not moving. However, in a velocity time graph, remember you're asking yourself, what is the velocity? And you can see for the period between 2 and 5 seconds that the velocity here, the purple section, the velocity is not actually changing. So the velocity is staying rigid at 4 meters per second. If the velocity is 4 meters per second, of course it's going to move because it's got a velocity that's not equal to 0. And it just means that it's traveling with a constant velocity, a constant speed. So if we're to go through the first 2 parts of this velocity time graph, we would see the panda. We don't know where the panda began, the origin, because velocity time graph is not concerned about position from an origin. All we know is that the panda accelerated and then went to constant velocity. So let's look at what that might look like. Panda's getting faster, and then going at that constant velocity of 4 meters per second. Okay, so let's look at panda in the section that is shown by a yellow arrow, so between 5 and 8 seconds. We notice that the velocity slope, which we have said that when there's a change of velocity it's equal to acceleration, we notice that the velocity slope actually slopes the other way. So we can see that there is, in this next part, there appears to be a negative acceleration because there's a negative slope. And we can also see that the panda's velocity changes from 4 to 0. So its velocity goes down. And this is caused by a negative acceleration. So again, if we want to look at this through, when we look at the 3 periods, 3 different intervals between 0 and 7 seconds, pandas, and we're going to show this in terms of panda movement. Panda accelerates, so from 0 up to 4 meters per second, then moves with a gradual velocity of 4 meters per second, and then starts to slow down to 0. Okay, from 7 to 9 seconds, we're talking this section here. which I'm going to show in green. Why not? So from this section here, we can see that the acceleration continues to be a negative acceleration. Now the panda had stopped, but now it accelerates negatively in a negative acceleration and changes the velocity from 0 to -3 out here. So the velocity is going to change from 0 to -3. Now we have a velocity in the negatives. A velocity is a vector quantity, and that means that velocity, by dint of the sign, whether it's a positive or negative, tells you the direction it's traveling in. So the fact that it now has a negative velocity means it's traveling in the opposite direction for the first time. So if we look at our panda, this will now start accelerating from 0 to 3 in the opposite direction, because now we're below the line, we're in the negative direction. And in a VT graph, your position above or below the line tells you whether you're moving positive or negative. Yeah, those directions could mean various things, could mean left, right, could mean north, south. But in this case, we're just saying positive, negative. The next section, which we're going to show in yellow, between 9 and 11, there is a constant velocity. And the final section, which we're going to show, we're just going to highlight that in black. We can see that the velocity changes from -3 and slows right down to 0. Now what caused that? Well, a positive acceleration. So remember, we're moving in the negative direction. Let's look at those last 3 sections. We'll say from 7 seconds to 14 seconds. So from 7 seconds to 14 seconds, this is what happens. Panda gets excited, smells maybe a little bit of bamboo somewhere back where they were originally, gets a wee bit excited, decides that from 0 there's going to be some acceleration to 3 meters per second. So it accelerates, starts moving faster, then continues at that 3 meters per second. And then there is a negative acceleration where it slows down to 0. Now, the panda didn't change direction for those last 3 sections because everything is below the line. So everything is in the negative, but it did move on that very last point. From 12 seconds, it moved with a positive acceleration, which means it was slowing down to 0. And you always look at the velocity that it's moving with, and ask yourself, in this point here, it was moving with a negative velocity. At this point here, it was moving with 0. So how did it get from that negative velocity to 0? Well, it must have accelerated. And in this case, it decelerated or accelerated with a positive velocity. Okay, so let's just look at moving from a PT to a VT graph. We're going to look at various sections just to run it through. Okay, first section, between 0 and 2 seconds, ask yourself what's going on. Just take a second to ask yourself. Okay, so if you said that the object was moving with a constant velocity at this point here, you would be correct. It is a slope, which is the position is increasing steadily over those 2 seconds. So it's a constant velocity. How do we find that constant velocity? Well, we said that we take the slope of this and we would get the velocity. So 6 rise over run, which is 6 over 2, and that would give us a constant velocity of 3. Okay, next section between 2 and 4, we can see that the position is not changing. It's got a horizontal line. On the velocity stage, that's actually going to be a velocity of 0. So we go straight down to the 0 line. Again, probably unlikely in the real world, but let's suspend truth a little bit here. And you are likely to get problems like this, so you just have to deal with them. Between 4 and 6, we can see that the position is changing. And that is changing in an increased fashion from beginning of that interval to end. We can see if we take those slopes that the velocity is getting bigger. Okay, so how would you know how to do this in a velocity graph? Well, we know that it's got to slope upwards to show an increased acceleration. So the question is, how would you show that line? What would that be? Well, if you take the slope at the very beginning and the slope at the very end, and you take those as figures, you can get a snapshot and an idea of what that slope would look like. So let's say, for example, the slope at this at 0.6 seconds was 10 meters per second. Actually, no, let's say it was 5, so I can fit it into the graph. That would show itself as from 0 to 5. Okay, so this is an increasing velocity. It's an acceleration pattern. Now, however, the velocity starts in the blue part, the velocity starts slowing down. We can see that the velocity starts getting decreasing. And what happens is you can see that the velocity is decreasing. And so there's acceleration in the negative to cause it to slow down. And eventually that acceleration means that this object stops momentarily, but then continues accelerating in the opposite direction. And we can see that by a movement in the line back towards the origin. Okay, so we can see that the velocity is starting to go downwards. So the velocity is starting to go downwards. And then at some point here, it actually starts moving in the opposite direction. So movement in the opposite direction would mean we move into a negative velocity. Okay, so once that object has started moving in the opposite direction, it goes under the line. Then the next part, the second red part, we have the object between 10 and 12, the object is not moving. So velocity-wise would be a 0. And then what's happening in this green section? Just take a minute to think about it. So in the green section, we've got a green line, and we've got a position which is moving steadily with a steady velocity between 0 and between 12 and 15 seconds. It appears to be moving with a steady velocity. Now we would have to calculate that velocity, and we can say that the slope of this is negative 6 meters per second. So we would need to expand on our VT, and we would show this down as a green at around here. We'll see our negative 6 meters per second. And it continues moving with that same slope. So it's still in the negative 6 meters per second. And then finally, we see a positive velocity. So there's movement back towards the origin with a positive velocity. And that is in the gray section. So between 15 and 18 seconds. So in that 3-second span, it moved between 0 and 12 on the position time graph. So we would get that slope, which is 12 divided by 3, which is 4. And this is a positive slope. So remember, just treat it as positive. And we would see that as 4 meters per second. So we can see that the object, whether it's above the line, below the line on the VT graph, tells you what direction the object is traveling in. And you can see that a horizontal line is represented differently, and a PT and VT graph means different things. So be very, very careful moving between them. Okay, so some questions you might get asked on a VT graph. Question number 1: What was the acceleration from 0 to 5 seconds? Well, in order to get acceleration, remember we look at the slope. Why do we do that? Well, it's rise over run. So if we just look at the units, it would be meters per second over second. And that's equal to meters per second squared, or the changing velocity against time, which is equal to acceleration. Okay, so if we take 0 to 5 seconds, we can see that it's rise over run. So 10 minus 0 meters per second all over 5 minus 0 seconds. And that gives us 2 meters per second squared, which is the unit for acceleration. So that means that the object was, every second, was increasing its velocity by 2 meters per second. Second question we might get asked is, how far did the object travel from the origin between 0 and 10 seconds? Okay, so in this instance here, between 0 and 10 seconds, how far did it travel? Well, we're not going to use slope for that. That just tells us the acceleration. But we can use the area under the curve to tell us how far it's after moving in that instance. So if we need to get the area under the curve, remember we can split this strange looking object up into a triangle and a rectangle, and we can find the area for that. So there's two different sections. Remember, for the triangle, we can use a half b times h, which to get the area of the triangle, which is a half 5 times 10, which is equal to 25 meters. Now, if we put in the units, you'll see that it is. You'll see that you start to get that. So it is a half of that, which is 25 meters. And the second part here, which is shown with the cross lines, we have length times width. Okay, so when you have length times width, remember you just multiply these two together, so it would be 5 seconds. I'm going to put in the units this time so you see that we end up with meters as our unit. So 5 seconds multiplied by the vertical, if you like, which is 10 meters per second. So if we multiply both of these together, what we notice is that the seconds above the line and the seconds below the line cancel. That's going to leave you with units of meters, which is what we want if we want to find out how far the object is after traveling. So this would be 50 meters. So the object between 0 and 5 traveled 25 meters. Between 5 and 10 traveled 50 meters. We're going to add those together and we get 75 meters. Now, it is important to note at this stage that if we talk about below the line, remember that the object is moving in the opposite direction. So if you wanted to get the full position that this object is after traveling, you would have to calculate all the different areas, and those above the line would be treated as positive, and those below the line would need to be taken away. They would be treated as negative. Okay, so we've learned a couple of things. We've learned that the velocity, a VT graph looks different to a PT graph, that the slope and a velocity time graph it gives you acceleration, that the area under the curve on a velocity time graph gives you the change in position of the object. So just to recap differences between VT and PT graphs. Well, on a VT graph, the vertical part, so the y-axis, actually tells you how fast an object is moving, not the location. A VT graph does not indicate a start position, an origin. It does not worry about that. It just is worried about and focused on the velocity and how the velocity changes. The direction is indicated by position on a graph, not the slope. So where it is on the graph, whether it's in the positive or the negative, will tell you the direction that an object is moving on a VT graph. And acceleration is indicated differently on each type of graph. On a PT graph, the acceleration will look like that. On a VT graph, the acceleration will be a straight line. Okay, that's it for VT graphs. We will continue our conversation in the next lesson where we'll move on to talking about AT graphs.